As an example, let's compute the typical drift speed of typical wires. For this purpose, I'm going to solve this problem. We have a copper wire with a 1 millimeter radius carrying a 1 ampere current. So these are typical values for the wires that we use in our homes. We are going to assume that the electrons are the charge carriers, and each atom contributes only one free charge carrier to the conductor. Of course, an atom has many electrons, but most of these electrons are bound to the atom. They are not free, but one of the electrons of each atom becomes free, just moves inside the material freely. So these are the charge carriers. So by using this information, we are going to compute the density of the charge carriers, of course. So let's just start with the problem. So we know the area of the wire. So this area is pi r squared. So therefore the current density has a magnitude given by current divided by pi r squared. Current is 1 amperes and the radius is 10 to the minus 3 meters. And so this is equal to 3.2 times 10 to the 5 ampere per meter squared. So that's a typical current density magnitude. Okay, next, we know the relationship between the current density and the drift velocity. So we have a formula where we multiply the number density of the charge carriers with the charge of the charge carriers multiplied with the drift velocity. So I know the charge. I don't know the density, so I only need to compute the density in here. Only in that case I can compute the drift velocity. For the velocity, of course, we know the direction, so it's opposite to the this given arrow in here. In any case, we just need to compute this magnitude, so therefore I'm just content with the speed. So therefore, once I compute the density of the charge carriers, I can compute the drift speed. So to compute the density, I need this information. So let's just go ahead. So the number density of the charge carriers is basically the number of charge carriers divided by volume. And since the given information says that each atom contributes one charge carrier, this is the same thing as the number of atoms divided by the volume. Okay, to be able to compute this, we can assume a certain volume. So, I mean, you can choose this in any way you want. There should be some methods that you're comfortable with, but I'm going to take 1 mole each. So as a result, I'm going to write number of atoms in a mole divided by the volume of 1 mole of atoms. Okay, so the number of atoms in a mole, this is known. It's just the Avogadro's number. I just need to find that volume in here. So to find the volume, of course, I can use density. Okay, so the density is basically mass divided by the volume. I know the mass of a 1 mole copper, it is 64 grams. That's given. That's basically 64 grams is the mass of 1 mole of copper. So therefore the volume can be found from this, because I know the density. That's basically 9.0 times, there's no times in here, it is grams per centimeter cube. So as a result, the volume is of 1 mole is 64 divided by 9 centimeter cube. So that's going to be 7.1 So I'm just going to write this volume in here, 7.1 centimeter cube. So the Avogadro's number is 6.02 times 10 to the 23 per mole. 7.1, I'm going to use the meter unit, so therefore this is 10 to the 6 meter cube. Each centimeter cube is 1 million, that's 10 to the minus 6 meter cube. And so therefore, if I divide this expression, I'm going to get a number density which is this is 8.5 times 10 to the 28 meter cube. So this is a value of around 10 to the 29 per meter cube. Right? These are the typical charge carrier density values for metals. For semiconductors, it's actually much smaller than this, but for metals, we have values around this figure. All right, I have inserted all the numerical values we have computed into this formula. And once we compute this numerical quantity, we are going to find the drift speed to be 2.4 times 10 to the minus 5 meters per second. Okay, so that's the answer, and it's an extremely small value. So for understanding how small it is, I have also expressed it in terms of the millimeters per second. It is 0.024 millimeters per second. So if I express it in millimeters per minute, that's going to be about 1.4 millimeters per minute. And if I multiply this numerical value with 60 again, I'm going to get distance traveled per hour. So that's going to be around 9 centimeters per hour. Okay. So this is strange because this is a very small value, and we need to understand why this is that small. Okay, so that's the question. Therefore, if the drift speed is of that order, it's about 10 to the minus 5 meters per second. These are typical drift speed values, by the way. Then how is it possible that when we turn on a light switch, the light bulb lights up immediately? So there's some kind of a contradictory picture in here. Okay, to answer this question, let me stress on this fact. We don't have a single particle in here. So for a single particle, perhaps we can talk about a single velocity. And so as a result, we don't need to discuss different velocities. But if we have a system of particles, in that case, the different physical phenomena are related with different velocities. So in this special case, for example, it appears that there are 3 different velocities that we can talk about. The first one is the drift velocity. So let me write drift speed in here, which is of that order of magnitude. It's 10 to the minus 5 meters per second. Let's remember that this is actually coming from the average velocity of charge carriers. Okay. And then we have the typical speed of charge carriers, the electrons, the free electrons inside copper. We have talked about this thing before. I have said that this speed is typically the same as the speed of the electrons inside atoms, especially the hydrogen atom. This is around the speed of light divided by 100. It's about 1% of the speed of light. So it's just an order of magnitude. So if you just compute it, this is going to be 10 to the 6 meters per second. This is huge compared to our senses. It's 1,000 kilometers per second. So they are moving very fast. Of course, they are not moving as fast as the light. And then there's a third speed. It's called the signal speed. Okay, I'm going to also describe what this thing is, but I'm going to say at the end that this is the same as the speed of light. Okay, but what happens is that let's at least compare the typical speed of the charge carriers with the drift speed. The picture is something like this. We have many electrons. They are moving with incredibly fast speeds, but they are all of them are moving in different directions. Okay. So these are the typical speeds. But when we are computing their average, of course, their average, when we take the average, of course, they cancel the effect of each other. So the average becomes almost zero. Only when in the current carrying state, of course, this average becomes non-zero. And in that case, the average becomes extremely small. So it's kind of reasonable that the average velocity has a magnitude which is much smaller than the typical speed values of the charge carriers. So this is reasonable. There is no problem with this. So in that case, in that sense, of course, the smallness of the drift speed is not a big problem at all. It's no problem at all because we know that, for example, if no current is carried, we know that the average velocity is zero, so the drift speed would be zero in that case. Okay, what about the signal speed? What it is? All right, I can explain it like this. Consider a long wire like that. This wire is filled with electrons everywhere. Okay. So suppose that you have made a change at this end by turning on the switch, for example. In that case, perhaps you have created an electric field in here. And as a result, this electron is pushed forward. So there is a force applied on that electron, which pushes it in the forward direction. So therefore, this starts moving. So we have said that the typical speed of this electron is about 10 to the 6 meters per second. It is very fast. But of course, this electron cannot reach to the other end, cannot move it in here, because we know that they suffer collisions. So there are many collisions in here. So therefore, this electron will be quickly randomized, right? Because of these collisions, that electron never reaches to the other end. And we know that if we take the collisions into account, the average velocity of this electron will be around the drift velocity. So therefore, the typical speed of the electrons has nothing to do with how fast that signal is propagating on the wires. Okay, so to understand the signal velocity, we have to actually understand what's going on in here. What happens is that when I apply an electric field in here, of course, all of these electrons will start moving. And as a result of this, there will be a charge pileup in here. Charge pileup. And so there will be a region in here which is slightly more negative. There will be a little bit more electrons in here. And we know that somehow these are going to, all of the electrons in these locations will almost instantaneously feel the effect of that charge pileup in here, because we know that there is a Coulomb force acting between charges. Of course, the Coulomb force does not act instantaneously. It acts with the speed of light. We will also say something about this at the end of the semester. So as a result, if you produce a change in the charge density in here, all the other electrons on the wire are going to feel the effect of that change with the signal speed, with the speed of light speed. Okay, essentially this is what we are seeing in our electric circuits. When I turn on the switch, the electron which is next to the light bulb almost instantaneously feels the effect, feels the change that has happened in here. Okay, so as a result, let's again reiterate, when we are talking about different physical phenomena involving many particles, we have to talk about different velocities. So each velocity is related to something else. So the signal speed, this is usually much different than the other speeds, like the typical speeds of the charge carriers and the average velocity. So in each case, of course, you have to know which velocity, which speed is related to the physical phenomena that you are interested in.